think we're good. All right, today we're going to move into the actual threaded fastener part of Chapter 8. So last time we did power and lead screws, which are threaded, but they're not necessarily used for fastening things together. So they're in the same chapter, Chapter 8 of Shigley, at least the 10th edition. I assume it's pretty common for most editions. But today we're going to look, or at the beginning of looking at threaded fasteners. So the point here is that we have something with some threads on it, and we are trying to clamp at least two things together. That's basically the goal here. Now there are a lot of paraphernalia that go with them. There's all kinds of types of them. Let's see if I can pick them all up. Some of them are named by their head type, you know, what kind of head's on there. Some of them are named by their size. Some of them are named by their thread type. And it's good to have a general idea of all these different things, because some people can name the same thing, like this one, for instance. This one, somebody might call a cap head screw, because it's got this little cap on it. Some people might call it an Allen head screw because the indentions in here are a Allen. Allens are also called hex keys sometimes, although you wouldn't really call this a hex head because a hex head tends to have a hexagonal shape on the outside of it. Some people might call this a socket head cap screw. You know, there's all sorts of things, and they're all talking about the same little screw here. And they're describing different features. Some people might call, oh, it's a fine threaded screw. And they might say this is a, I don't know, M5, I don't know, 1.5 maybe. I don't know what the thread pitch is on this thing. But, you know, and they're all talking about the same thing. So it's good to have a general idea of what some of these terms are in the book. And as far as what we're going to talk about, we're really kind of talking about this kind of screw for the most part. So not a screw at all, a bolt. So that's another thing, is when do you call it a bolt and when do you call it a screw? In general, you're going to clamp things together with a bolt. Certainly if there's a nut on there, you're pretty much always going to call it a bolt. But there's sometimes when the nut isn't on there, and the bolt just screws into threads that are in the part that you're, or one of the parts that you're clamping. Maybe this part has a hole and this part has a threaded hole in it, and you bolt it together. And so that could also be a bolt. But a screw is going to be generally not going to have the hexagonal head on it. That's usually, if it has a hex head or something like this kind of hex head on it, then it's going to be a bolt. And screws are going to have all sorts of different heads on them. Now this one is a little special. It does have a hex and a slot, but the threads on it aren't at all like a bolt thread, right? So this is actually a masonry type of thread. You can tell by, I don't know if you can tell on the screen. Let's see if we can make it. Now you might be able to tell. See if we can get them side by side. So the bolt threads are similar to the Acme threads that we looked at before, but they are different. Let's see if I can, here's the Acme thread, or trapezoidal threads, which are essentially Acme threads, just slightly, ever so slightly different. So this was the lead screw with trapezoidal or really close to Acme threads. Here's bolt threads, and then this is a masonry thread. Let's see if I've got some others out here. Here's a generally used for wood, this kind of thread. I thought I had a plastic screw somewhere. It's disappeared on me. I don't see it anywhere. Well, a plastic screw will have threads similar to the wood screw, but they'll generally not have quite such a root diameter here. It'll be generally smaller and really wide threads because it has to bite into a pretty soft material in general. Let me see if I can find one really quick so we can see it. I did find one, but it's not quite. I don't know if you can pick up on it. This one does have a little bit larger root diameter than some of them when it's a plastic screw. But that kind of thing would also be plastic. It's kind of maybe hard to tell. They're usually not quite as pointy as the wood screws. This one, let's see if this, no, this one has kind of a nail end on it, so you can get it started. I don't have one of these, I couldn't find one handy, but there are some screws that are self-tapping, meaning they almost have a drill bit on the end of them so that they can drill their own hole as they go in. Usually that's going to be a sheet metal screw of some sort. Let's see if I've got any other types out here. I have other types of other heads, so that's another thing. This one, let's get these out of the way. This one might be, someone might call this a flat head because of the head being flat across here compared to something that's rounded. So this one might be, this one's a little bit ambiguous because it has a little bit of a shoulder right here, which some people might make this into a pan head, and then it's also very rounded, which some people might call round, although round is usually, I would call this one a pan head. So it's got a little shoulder and a rounded top, and I would call this one rounded. Oh, wait, that's under me. Here, let's put it over here. This one. So rounded and pan head. And then this one being flat. Some people would call this one countersunk because it's got this little taper under it so that when you drill it in, if you've countersunk the hole, it can fit flush with the surface. I don't have an example of a countersunk hole, but it basically matches that shape. But what I was going to make the point of this one, this is usually not called flathead because I don't know if I brought a flat. No, I don't have one that I'm talking about with flat head. But it's slotted. It just has, instead of this is usually well, let's see if we can get it to not shine so much. This little cross in here, a lot of times people call that Phillips head. And then one that just has a slot across it is either slotted, or some people might call that a flat head, talking about the kind of screwdriver you're going to use. So one that's got a flat head on it, or one that has this cross like a Phillips is the other name for that. So there's lots of different things that you might have to work your way through. You have washers. There's a really big washer. This one has a couple of washers on it. You have washers that are slotted. So this one has a circle, but then it has a slot cut in it so that it can kind of compress. And these are used for when you want something to lock together, and the washer itself kind of helps hold it together. So maybe there's a big vibration that you're dealing with. You've got the nuts, and you have nylon nuts or nylock nuts. So there's actually a little ring of nylon material in here. See that little bit of different color? And so that also helps this nut not back out, because when you screw it together, the bolt is actually going to cut into this nylon and form its threads as it's passing through there. And so there's all sorts of accessories and head types. Well, we didn't even talk about fine threaded and maybe coarse threaded, although this one probably is also fine threaded. Where's something that's really coarse threaded? Well, you wouldn't really talk about a wood screw being coarse threaded, but the distance between the threads will be talked about as either fine threaded or coarse threaded. Fine ones being the threads are really close together, and coarse, the threads are further apart. This one's pretty rusty in there. Even this might actually fall into fine threaded, though we would have to measure to see what it actually is. But it is certainly more coarse threaded than something like this. So you have screws, you have machine screws, and you have bolts. Those are the big categories, and we're mainly going to talk about bolts. So let's look at those. I just want you to know that there are all sorts of terminology to be aware of. Terminology for naming things, naming parts of the bolts and screws. So there's a lot of stuff to make yourself familiar with when you want to talk about fasteners. Let's get most of these out of the way. We can leave this guy. Let's leave that, and let's get rid of all these for now anyway. All right. So the bolt, and a lot of times you have bolts and washers. I just didn't go find washers that fit this particular bolt right away. Let's screw this on so you can tell which is which. All right, so you have the head, usually a hex when we're talking about bolts, meaning that there are 6 sides to it. There might be an indicator, so this says 4.8. Depending on where this one was made, this one has indicators that are little lines on it. There will be some way, if it was made in the United States, and you're in the United States, then it's going to have some kind of indicator of the strength of the material. We have a chart in your book, 2 charts actually, that kind of describe how to read these. Let's see if I can find one real quick. Might have already passed it up. I'm looking for it. Here it is, or here's one of them. So you have charts like this. So this one had the 3 lines across it and then a manufacturer's mark, I think. So it would match this, which is a SAE 5 grade, so kind of middle of the road in strength. The grade 1, actually the grade 1, 2, and 4, you can't really tell the difference from the head because they don't have marks on them there. But then as you get higher grades, then you are assuming that you've chosen this higher grade because you need higher strength. Look at these minimum tensile. Well, let's look at the proof strength, minimum proof strength. Maybe tensile because you don't know what proof strength is necessarily yet. So you know what tensile strength is. And look, they get gradually higher as you get more and more marks on these things. And they get obviously more expensive too. And so the grade is probably important in a machine design because you're expecting a certain tensile strength, which is related to the proof strength. The other one I had an actual number on it, 4.8. Let's turn it the right way, 4.8. And there's that's just a metric mechanical property. So 4.8 is generally used on M1.6, so pretty small, to M16. This is a M10 probably. Yeah, I would say that's an M10. Which is in that range, and then it has a certain set of strength characteristics. Same thing with it, that they get the grades as the number get larger, the strength gets higher. And then there's other sets over here, ASTM type of sets over here that you can tell. Again, not every bolt is going to have a mark on it. Here's one that doesn't have a mark on it, so either this one wasn't made in the United States for sale in the United States, or it's one of the really, really weak ones. So, you don't really necessarily know when they're not marked. So in that kind of situation, you are either saying that bolt is not going to really be carrying that much force in it, or it's not that important, or whatever. We just need something to hold these parts together. Whereas the ones that are going to have certain marks on them, you're aiming for, you need at least that much strength. So you can always use a stronger bolt if you end up needing to, but you wouldn't want a weaker bolt. So you have these marks on them. We have these thread profiles, like we talked about a little bit, and I didn't talk too much about them, but there are, in your book at least, we're going to go with 2 basic thread profiles, the UNC and UNF. So UNC is unified coarse, UNF is unified fine, and both of those are going to be listed out, some details about them which we'll need, not today, well actually maybe today. They're going to be listed out in this chart, table 8.2, which we're really zoomed in on. And you've got this table 8.2 is just for US measured ones, so this isn't a metric table. There is a metric table on the next page, table 8.1 though, that has some information also, and it just doesn't on the other table. It just says coarse and fine. This table it says UNC for unified coarse, UNF for unified fine, and again that coarse and fine is threads per inch. How many threads are there per inch? Obviously, in the metric, you don't measure threads per inch. So you've got information here about these diameters, the tensile stress area. So these tensile stress areas are when the bolt breaks in the in the thread somewhere, which is not necessarily one of the more common places it's going to break. But if it breaks in here, then that would be that area. The area in tension. So it's similar to the root diameter, the area at the root diameter. It's similar to that, but it's actually determined through testing. So we do need that just to figure out what area is carrying this tensile. Bolts are going to be in tension when you, let's see, I've got this thing over here we'll look at in a minute. We've got two pieces that we want to bolt together, and as you turn the nut, normally you turn the nut, you don't normally turn the bolt head. But as you turn the nut, then you're stretching out that bolt to a certain point. And depending on the type of connection that you're trying to make here determines how much you turn this nut. So, and there's literally one mechanism for measuring when you're done. You might have seen a torque wrench, or might have even used a torque wrench before to set the amount of torque that you're applying to this. That's actually the least precise way, other than just by feel. The most precise way to determine when you've tightened this enough is to actually measure how long the bolt has gotten. Because as you're tightening this, you're stretching out the bolt. And so the most accurate thing you can do, if it's super important and you can get to both sides, get some kind of measuring device across the bolt itself. So measuring here, and as you tighten this nut, you're stretching out this section and you're making the whole bolt longer. That's the most accurate way to tell when you're done. The second most accurate way, well, there's some other in-between ways, like there are bolts that have little indicators in the head that change color when they've reached a certain tension in them. There are things like that that are not very common, but maybe you can't get to both sides to measure it, and you can only see the head of it, and there are some indicators like that. We're not really going to, other than what I just said, we're not going to really talk about those. The second most common way that you would do this is actually by you tighten the nut down until it is snug, and then you turn the nut a certain number of revolutions. So you might see it as half turn past snug, or quarter turn past snug, or however many revolutions or parts of revolutions you need to turn it to induce that clamping stress, or it's called preload, in the bolt. That's the second best way to do it. The third best way is actually use a torque wrench. Torque wrenches can be, notoriously, you can cheat them. Like you can jerk on them and they'll click, or the indicator will reach the number you're trying to aim for, and you didn't at all apply that kind of torque. They also are subject to, not only are you measuring the torque that is getting applied to stretch the bolt, but you're measuring torque that is being used up, I'll say, in friction in this washer or beneath the nut. A lot of times you don't necessarily have washers beneath nuts. I just put one here. So there's friction that is also included in there, even if you're carefully, turning it. So torque wrenches are actually probably the third option. And then the last option is just tighten it until you can't tighten it anymore, or whatever. So that's, it might sound like torque wrench is the best one because you've got an indicator right there that says how much torque you're applying, but in very precise situations, that is actually not the best option if these others are available. You can't always go measure the change in length. The turn of the nut is actually usually a pretty good one, because no matter how much friction is involved in the thing, you're still turning the nut a certain amount. And that amount of turn, combined with your knowledge of the pitch of the screw, will tell you how much you've stretched the bolt out. So it's very deterministic that way. There's not a lot of other things going on. There are tiny things that we'll talk about, but not that much. All right, so what else do we have? We have obviously the head, the nut. This one has a threaded region and an unthreaded region, so this will be the shank. This one does have some washers on it. Washers have a top and a bottom. Did you know that? We'll have to see. Maybe if I put these two side by side, you can tell the difference. And let's just look at them really close. I think you can tell the difference. So the way washers are made is they're punched out of metal sheets, and the direction it was punched creates this rounded edge. So you can see that rounded edge on this one, and this one is very sharp. So these are the top, and this side is the bottom. So the bottom needs to go against the thing being clamped, and the rounded side needs to go against the head of the bolt. And then if you have a nut on the other side, the rounded side needs to go towards the nut. I don't have a nut for this one. Well, I think this lock nut fits it probably, but we're not going to be able to tie it on there very far. So like that, with the sharp edges on the inside. Looks like these might be a little bit large for these. I don't know. But you know, your instinct is that these washers are here to kind of spread out the load, which they do. You know, there is the clamping force. This particular nut has a washer face under it, right there. You can kind of see that circular edge. I don't know. You can kind of see it in that one. There's a circle around there, so it has a washer face, which does kind of even out the distribution of the load. You really wouldn't want these corners, like this one doesn't have a washer face, so you almost have to use a washer with this one, because you wouldn't want these corners of the hex head digging into the material that you're clamping. It's going to scratch it up or create little stress concentrations where it tries to dig in on those corners. So this one really needs a washer. This one does have a washer face. But when you apply a washer to it, obviously you do spread out the load a little bit more. Generally, you take 1.5 times the diameter of the bolt diameter here, and that is how much the washer the washer is going to spread out the load. Now this one, I've got some much larger washers on it, so some oversized washers. It's kind of blowing out with the camera. That's a little better, I guess. So this is an oversized washer just for something we're going to do later. But there's a little fillet underneath here. Let's go back in. Little fillet. You can kind of see a little fillet in there a little bit. And so that fillet is one of the more common failure points. Because it is a fillet, you know, there is a transition. And if you don't have a washer, that makes it worse, because the fillet can get caught on the edge of the hole. If you turn the washer upside down, now you've got this sharp edge of the washer on the fillet here. So that's even worse. So you really do want the washers their correct orientation. Another common failure point would be wherever the threads start. Now on this bolt, the threads start or end, whichever way you want to think about it. It was threaded from this end forward, so this might be the thread end, I guess is what you actually would think of. That coincides with the fillet, so that's a double whammy on this one. This one, since it has an unthreaded region, has threads that end, you know, right in here. You can probably see the lead out right there. And so this is a common point of failure. This is a common point of failure. And then whenever you finish clamping, that first nut or the first thread in the nut is also a common point of failure. We talked about last time with the lead screws how there was 38% of the load was carried in the first thread, 18 in the next thread. I don't remember what the third thread is, but it was smaller. And same kind of thing happens here. That first thread takes a larger portion of the load. The next thread takes a smaller portion. and then the third thread takes pretty much what's left. I mean, there's tiny bits. In the Acme, it said that there was, by the seventh thread, there was no load at all. And so the same kind of thing happens in a nut. Now, one thing that's different in a nut is that you are clamping things. So part of the clamping is that you don't want to yield the bolt necessarily, but you do get it really, really close to yielding. So you will actually deform the threads on the screw that are in the nut and the nut itself. In fact, on higher precision hardware, which this is not, the threads between the bolt and nut are intentionally made with slightly different pitches. So I think the threads on the bolt would be a little bit finer pitch than in the nut, so that this deformation happens, and then as it's happening, the pitch between the bolt and the nut actually start to line up so that it can kind of more evenly distribute that load in the nut. You're not going to find that without some special order. It's not going to be the nuts and bolts at Lowe's. So those are much more precision. Generally, you're assuming that that first thread that's in the clamping region here is going to take most of the load. That brings up some other terms. Grip. So anything from the bottom of the bottom of the head of the bolt to the inside, I guess we can call it top of the nut, is called the grip, including washers. So if you have washers in there, then even this washer would be part of the grip. And the grip is measured from under the bolt head to above the nut here. So these washers would be in the grip. And that grip, in this case, it's this washer, this piece, and this washer. Oh, wait, we're too close to see them all. There we go. And so the grip would be the washer, this piece, and that washer. However long that distance is, that is the grip for this bolted member here, or two members. You have a page that's really useful in your book, once I find it. Oh, like I was talking about the different head shapes and everything. Your book does go through and kind of describe them and give you some others over here, but that's not what I'm looking for right now. I'm looking for this page, so we might have to zoom out. We are zoomed out. It's just a lot of stuff on this page 418 or table 87. I assume in most editions of the book, the table number is probably the same. Page number might be slightly different. What this page does is it gives you two scenarios for fastening at least two pieces together. It can be more than two things bolted together. You can have 3 or 4 things bolted together, but in general, there's 2 things bolted together. It shows one situation where you have a bolt and nut, and the bolt goes all the way through. You screw the nut on the other end. This one actually has a washer on the nut side, and they're just using the washer face of the bolt on this side. This one actually is hard to read. You have to look at it really closely. Let's see if I can find my pointer. Maybe we can even zoom in, because it is, there we go, we can see now. This little piece right here, see how it doesn't look like all the others? Those little angles, that's showing the end of the bolt. I really wish they'd have colored this section different or something. Maybe I could even do that on mine. This part is not the bolt. This is the hole. The hole goes in the dark gray, there's just a hole. In the light gray, there is a threaded hole here, and the bolt goes through the dark gray. You don't want the threads in the part that's being clamped to the other part, because it needs to freely slide through this part, and it screws into or bolts into this part. And so this one is, you may or may not have access to the other side. This one looks like it's a through hole, but it could be a dead end, so not a through hole. If possible, you want through hole so stuff doesn't get packed down in there, but you don't always get that option. So this one would be the case where the bolt doesn't have a nut. All the threads are in the bolting or clamped piece, in one of the clamp pieces, the one on the other side of the bolt head. And this one is just being squeezed to this one. So there's no threads in this one. It does have a washer here. And all these little L's, LT, D, all these things they're actually described on further down this page. So there's a lot of definitions down here, some are on the next page over here, but these are all the links that you might need when we're calculating what we're going to calculate. So today we're going to calculate stiffness of the bolt itself, the fastener, and stiffness of the pieces being bolted together, and the combination of all of that. So what ends up happening, and it might be easier to think of with this one, is the more you tighten this nut, the more you stretch this. So I'm stretching a piece of metal. It's a spring at that point. It's just a really stiff spring, because it's basically this solid, this solid piece here. This one, if I'm tightening this, I'm stretching this portion and this portion, which this one does not have threads. This one does have threads, so they have slightly different spring rates. So I have to add those together. This one is just all threaded, so I wouldn't really have to do anything different with it. It's just one spring rate in there, unless you really want to get picky and say that there's a tiny little section up here that's not threaded. I don't know that you want to be that picky though. Make it a little brighter. All right, so this spring here, as we pull on it, it's not a very efficient spring, I guess, but you do apply a tensile force and stretch this out so that it does have a spring rate. It's just, again, it's millions of pounds per inch spring rate. And at the same time, you're compressing the things you're clamping together. Now this one, I want to show you why I've made this here. And actually this one we might need to make even brighter. So remember, we're stretching the bolt. It's a spring. We're compressing these clamped members, and they are also really stiff springs, even stiffer than the bolt is. But we're compressing them. But the bolt only has so much influence. It can't, if I'm clamping here, then I'm not really compressing something that's over here, or even on the edge here. I'm not really compressing this part too much, other than the fact that I'm pulling the whole piece of metal together. So there's these zones of compression that really determine the spring rate, and that's what is inside here. So this shape here, this is two shapes actually. Let's take it apart. Kind of screwed it together pretty tight. Oh, here's the nut over here. All right. So these shapes are called frustum. So it's sort of like a cone with a hole through the middle, and we've chopped off the top. And I have two of them that are, in this case, identical. They're always going to be identical, but it's not always quite as simple as that, because these could be different materials. They could be different thicknesses. No matter the material, thickness, all that kind of stuff, these end up being this shape where you go to half of the grip, so whatever that is, and one half looks like this shape with this is a 30-degree slope, and the other half looks like a mirror image of that. It just might be that this point here where they become mirror images of one another may not coincide with the same point on the parts here. So in here, they become mirror images, like basically the red one goes in here, the blue one goes in here perfectly. But it could be that this is 3 or 4 times thicker than this one, and then you'll have, if this is really thick, then these things, I should have made an example of that one. Maybe I'll have time to print one so we can show it tomorrow instead of just trying to describe it. Then the part where the mirror image drops down, and this one is all red, this one would be blue, and it would have part of where the red starts to taper back in. There's kind of an image in your book that describes that. Well, here it is. So here, notice how the bottom part is thicker than the top part. So the clamped piece on bottom is thicker than the clamped piece on top. The two frustum, well, actually when you do plural it's frusta. So two frusta still, and it almost fits right, but they are still half of the grip. So the grip in this case would be from here to the top of this washer. The washer is in the grip also. So they're half of that, but it turns out that the top half it crosses over this boundary, right? Because you literally take half of 3/4, 1/2 plus 0.095. Half of that is where the mirror image happens. And so that's why they've got this top frustum actually exists between the light gray, and a little sliver of it is in the dark gray. We'll talk more about that when we actually solve one of these things, and I'll try and maybe I can print one. Actually, I don't know how I would print it though, because we couldn't put it together. We'll have to figure it out. Anyway, let's do the simpler stuff first, and then we'll work our way up to these things. So let's say we've got this. Actually, let's rebuild our deal here. So we've got, this is a model of a M10 by 1.5. So the 10 means it's a 10 millimeter diameter screw. So 10 millimeters across here. 1.5 means there's 1.5 millimeters between consecutive screw threads. Remember we had the double starts and triple starts and quad starts and all that on the lead screw. You don't really have that on bolts and nuts. They're pretty much all single start. Then we have a washer. Then we're going to have another washer just because that's the way I made this part. And then we will have our nut. There we go. All right. Now, and so we're clamping this thing. Now in this one, you really should have about 2 threads sticking out, 2 or 3 threads of the bolt sticking out past the nut. So this bolt is technically a little bit short. It needs to be a couple of millimeters longer, and because you don't want a location where there's first of all, you're not getting all your strength. You know, there's a little bit of strength left. You got most of it by having the 3 threads engaged, but you did leave a little bit behind. Second, stuff can get packed in here, dirt and grease and all that, and cause problems later on. Also, you don't want the bolt sticking out like an inch or anything, because then it's going to be a hazard for working around it, because you got this thing sticking out of here. So about 2 or 3 threads sticking out. When you are designing these, you measure, you know, the grip, you measure what kind of washers you're going to use, the nut, add all that together, and then you add a little bit more so that it can actually stick past the nut. But you don't necessarily order that exact size of bolt unless it is super important that you do. What you do actually is you pick a standard size. So there is a little chart. See, it's in the back of your book, 1047 maybe. Let's see. No, not 1047. Not that. 1043. So this table A17 on page 1043 gives you a list of standard lengths. Now, this may or may not be the list of standard lengths that your particular supplier carries. So all of these tables that we're looking at here, you don't necessarily go back to the book and look up numbers out of the book. These are sort of generalized. In some cases, they are from manufacturers, but are those the current standards? You know, the book is some number of years old, so it's not a good idea to go into the book and use the numbers in the charts when it's a manufactured thing, You know, using like stress concentrations out of the book and, you know, things like that is kind of expected. But when it's a manufactured thing, you really need to go to your supplier and look at those same type of numbers from that supplier. So this is just kind of giving you the idea of what you would find at a supplier. They have certain lengths of bolts or fractions of sizes of whatever it is they're making, and these are typical fractions. So this was a 55 millimeter bolt, I think, and it's a little bit short. So I'm assuming that 60 would be the next one up. Let's see. 50. Well, actually, they don't even show 55 in this chart, although I did find McMaster. This is a model from McMaster that I printed. So there was a 55 there, but 60 is the next size up in this chart. So when we're doing coursework, we're going to refer to this chart for our standard lengths, but in the real world, you may not have this many options, or you may have more options. What you don't want is to specify, I need a 53.48 millimeter length bolt. That's probably not going to be, unless it's super important that it is exactly that length, that's probably not the best route to go when you're the designer. All right, so that's on page 1043, table A17 is our standard sizes of stuff. All right, so we bolted this together. Where are we at on time? We got time for some stuff here. If I don't finish all of this, I'll do like I did last time and add a little, just a walkthrough of the calculations of just the calculations. And if you didn't see that, I did do that for the for a lead screw. I used the Ender 3 printer's lead screw, and we went through calculations of how fast we can move the z-axis based on that lead screw. We also calculated the stress on it just to do it, although there's almost no stress on it. All right, so I'll do that same kind of thing if we don't get through all of this in here, or if it needs to be redone for some reason. All right, so let's start with the bolt. So this particular bolt did not have a unthreaded region. It was all threads. So I'm going to bring up MathCAD just so that we can look at a little bit neater when I'm writing things out. And we'll have to switch back and forth between MathCAD and the page over here. All right, so we want to do the bolt stiffness. So this is on page, let me find the right page. Page 419 kind of goes where they're deriving the bolt stiffness. So let's look at that real quick. So here, they start out, the K is spring rate, and this derivation is for this kind of bolt that has a unthreaded region and a threaded region. So we can use it for one that's completely threaded, just anywhere the unthreaded is, we will zero that out. So what this kind of bolt does for us is it is one spring in series with another spring, and that's what they're doing right here. Springs add in series with the reciprocals. So they've rearranged it here. These springs, in this case, they probably should have the same modulus of elasticity from one end of the bolt to the other end of the bolt. That would be a really strange screw if it did not have that. So that's what they're showing here, is they're calculating the spring rate of the threaded part and the spring rate of the unthreaded part. And I think they're using the T for threaded and D for diameter for unthreaded. So threaded on this side and unthreaded on this side. So AT, that's the tensile area of the thread. So that's one of the numbers that you have to go look up in table 8.1. Back a couple of pages. Several pages, actually. It's actually in the section with the lead screws, which always confuses me why it's there. But that's where they put it. So for ours, we have an M10. We had a 1.5 millimeter pitch, meaning that there's 1.5 millimeters between consecutive threads. And we have a tensile stress area, AT, of 58 millimeters squared. So let's write 58 millimeters squared for AT on our MathCAD. Oh, I'm not. Oh, yeah, there were. AT 50 millimeters squared. I don't know if it's going to give us the, it does give us the AR minor diameter, but normally for the other area we need is AD. Normally you just actually take the 10 millimeters and calculate the area. So we'll do that. So AD is going to equal pi D squared, and we can put D in a second, over 4, which it doesn't currently know the diameter. So let's move these down a little bit. So this is a 10 millimeter bolt. So there we go. I don't want it in meters squared though. There we go. And that makes sense. It's a little larger than the threaded region. So that makes sense. Then, other parts of the equation, we're going to need the modulus of elasticity of this material. So E, and E is going to be dependent on what material we're using. Let's just see if we can find a good value for that. Obviously this is plastic, so that's not going to work. Although there are plastic and nylon fasteners. I thought your book had a chart that had, I guess it just shows you the strength. We'll have to get modulus of elasticity out of the back of the book. Let's just grab it from this one. This is a, grade 5, and it has 30 million PSI. Now we're in the metric system. MathCAD doesn't care about that. MathCAD just wants as long as we put the units on there, it can handle that for us. So let's just say that's a steel bolt, and I think that's 200 megapascal. Let's just put it in 30 million. All right, so MathCAD will handle our conversion for you. In fact, we can do it this way. Yeah, it was 200 million megapascals. All right, so good enough. Let's see. We need the length of the thread. So this one you have to be a little bit careful on. So pretty much if you have one that is unthreaded, you definitely need the unthreaded region to exist totally in the grip, right? If we've tried to bolt these two pieces together with this bolt, put the washer down there, we couldn't do it because the threads end way back here. So we couldn't run the nut up far enough to actually clamp it. So the threaded region exists in the grip. Now, also on top of that, in general, you want the threaded region to go across this gap right here, where the two pieces are clamped together. You want that to be unthreaded instead of having the threads go through there. Now, in this case, the threads are going to, there's no option for that. The threads have to go through the gap here. Why you might want to avoid doing that is if this has not only forces trying to pull it apart, but forces trying to shear it, it's better to have that shear force on the unthreaded part than the shear having to be carried on the threaded part. The threaded part is smaller a little bit, and it has these really high stress concentrations from the screw threads there. So if possible, if you think this is going to have shear on this join, then you want the unthreaded part to be across that shear plane. In this case, that's not an option because our bolt is like this one that is threaded the entire length. So to get the length of the threaded part, we're just going to measure, it's the length of the threaded part of the grip. So the grip, again, is going to go all the way from the top of this washer, so under the head of the bolt, to the washer bottom on this one. And top and bottom is kind of relative to whichever direction you're looking at it. So we need to measure, and I don't think my calipers can reach across there, so we'll do it a piece at a time. So we need to measure this 20, well, it's 20 millimeters. We need to measure the thickness of our washer is 5 millimeters. So I've got Let's draw it out so you don't have to try and remember it all. All right. So we've got the head of the nut. We've got washer. We've got the clamped piece number 1. We've got clamped piece number 2. We've got washer. And we've got the, I think I said nut there. That's the head of the bolt. This is the head of the nut. And then hopefully we would have a couple of threads sticking out. And the bolt goes through here. All right, so the grip is going to be, we measured this as 5 millimeters. We measured this one as 20 millimeters. We didn't measure the other one, but it's also 20. I printed the exact same thing twice. And then this is also the same 5 millimeters. So we have 50 millimeters of grip, and that's the LT in this equation here, the length of the thread in the grip. So you don't actually go measure the bolt because, you know, some of the threads are likely to be not in the grip. So LT for us is 50 millimeters. Okay, we have E. Now here's the actual equation where they've combined the threaded and unthreaded portions right here, KB. So KB is the stiffness of the bolt, like that. We have all of these things. We didn't do LD, the length of the unthreaded portion in the grip. We'll do that. It's 0 for ours because it was threaded, fully threaded. They're both threaded and unthreaded have the same modulus of elasticity. We have our diameters. So I think we are good to go now. All right. So let's go over here and build our equation, KB. So the stiffness in the bolt is equal to the area of the unthreaded portion times the area, oops, clicked on something wrong there, of the threaded portion times our modulus of elasticity of the bolt material divided by the area of the unthreaded, which is going to be 0 for us, times the length of the threaded portion plus area of threaded times length of unthreaded. And we have to put in here that our LD 0 millimeters. And we might have to actually measure it to get, because it is like a millimeter or something. But here's what we have. Kilograms per second squared, probably not the units that are going to make much sense to us. Let's do newtons per meter. Oh, you know what? Why is it? It has megapascals. Why is it giving me these weird units? I don't want that in there. There. Kilograms per second squared. I need another. I've got a unit messed up somewhere. I wonder if it's in the fact that I'm using PSI. It shouldn't matter because it converted it to megapascals. Yeah, it didn't. That's not the problem. I'll have to look and see why MathCAD is angry with me. I'm pretty sure I wrote the equation correctly, but there's some weirdness with why it's not put in. It's giving me kilograms per second squared instead of a stiffness. I'll have to look and see. Anyway, that would be how we would calculate member stiffness. Not member, bolt stiffness. So all this would be once we get it right, is the stiffness of the bolt itself. So the spring stiffness of the bolt. So now I've got, if we were to draw a picture of what this kind of looks like, we have the, let's use different colors. We have a spring. I guess this kind of looks like threads on it, but this is going to be its spring. So there's a spring here for representing the bolt, and we just calculated stiffness, although I've got something kind of messed up in the calculation there that's giving me units that are weird, but that's okay. So I've got the spring of the bolt, and I'm turning this nut down here and stretching out the bolt, so it's in tension. So I'm actually stretching it out. Now we need to do the same thing for the clamped pieces. So for now, let's just draw them as a big spring over here. So this big spring is actually being compressed. So I've got a preloaded stretch in the bolt and compression from the bolt being stretched transferred to the clamping. And remember, I'm dealing with this shape of region that is springy in the members, so in the plates here. It's not quite as straightforward as the nice cylinders that I had for the bolt. So the equations for calculating this spring rate are a little more complicated. Your book goes through several of them. Oh, I bet it's because I have that 0 in there. Hold on just a little second. Let me look at something. Nope, that didn't care. I'll have to see what's going on. All right, anyway. It's hard to try to figure things out while you're talking about them. All right, so this, well, actually over here, starting over here and using these diagrams. So there's a little explanation in here about what shape to use for this. And they go through a couple of different talks about this pressure cone. And they mention that that's really complicated to do it this way, the Rockster's pressure cone method for stiffness calculations with a variable cone angle, which may be more accurate, but your book goes through and says they did some finite element, or Osgood did some finite element analysis and came up with a range of cone angles, so the angle here, so alpha up here, and found that 25 to 33 was a good range for that cone angle. And then in the book, they're going to use alpha equals 30, except in cases in which the material is insufficient to allow the frusta to exist. So if you had something like a sleeve that you were bolting together and it's just not, the cone goes outside of the sleeve. You know, if you just had a sleeve, meaning like a cylinder that you're clamping together, which does happen. There are plenty of linkages, even in an automobile or somewhere where you have a sleeve that's connected to a rod or whatever, and you're clamping on that sleeve. That frustra can't develop because it would actually be outside of the sleeve. So in cases like that, don't do this process, is what they're saying. But in cases like this, where, you know, the frusta, both of them, will fit within the shape of whatever's being clamped, then this method works. And not only that, but you're going to use a 30-degree alpha. So the slope of this line, or this line, is 30 degrees. And then they go into the derivation of how you get the equations. So it's worth, you know, looking through, kind of getting an idea of what they did. Basically, they did some integrals of rings that create this shape. They even mention here they have to look up the integral in a table of integrals and things like that. And then they get to over here. And you have a set of equations that you can choose from to use each one has a reason why you might or might not use it. So this first one is just the general solution. So it will always work, assuming you have the case where the Frusta can be generated. You know, you're not doing the sleeve or whatever. Then this one will work. And basically it's based on the material modulus of elasticity, which in this case, you do have to be careful because these two pieces may not be the same material. You know, in a bolt, you're pretty certain that the bolt's all the same material. But these two may not be. That one might be aluminum, this might be cast iron, and then you might have a steel washer on one side of it. So your grip is made up of 3 different materials. So each material is going to have its own version of this equation. All right, so this is the general equation, though, that you can apply to one piece of a frustum that has the same material. And then you've got all these D there and T, they're all shown in this combination of diagrams over here. So D, the uppercase D, is the, typically it's the washer face diameter. So it might be that you don't have a washer and it's just the washer face for the head of the bolt. Maybe you do have a washer and you don't know the diameter of it, or it's really, really wide and kind of oversized. In those cases, you use 1.5 times the bolt diameter, not the head diameter, but the bolt diameter here. And I think your book even mentions that somewhere in here, right here. The washer diameter is 1.5 diameter. Sometimes you might be working with a portion of one of the frusta, like this piece here. And so in that case, you pick the diameter, uppercase D, as the smaller of those two. You know, in that case, it would be this 1.437 number from here to here. I'm talking about this little sliver. So that's D. Lowercase d is basically the bolt diameter. There is some amount of clearance between the bolt diameter and the hole that the bolt goes through, but typically you just use the bolt diameter. T is the thickness, so you know it's how thick is it. I'm trying to hold too many things. How thick is it this way? And again, you might have the case like in this one where this one, the thickness for this darker one is this really thin 0.775 inches. All right, so that's this equation. This one can be used if we have a situation like this, where they are symmetric, and basically the plates that you're clamping and the combination of washers is symmetric about a center line. In that case, you end up with 2 frusta that are exactly the same, and you can calculate them with this equation. So it basically goes in and it combines a couple of things. You can now see there's the washer is included in there. There's your angle for the alpha equals 30 degrees for what we're using. And they've combined a couple of things together. This one, they went a little bit further. So this is an iteration of this equation where they go ahead and plug in that, okay, in this book, we're going to use alpha is 30 degrees. So you don't see the alphas anymore. The tangent of alpha has all been evaluated. And they said that the washer diameter is just going to be 1.5 times the diameter of the bolt, because that's pretty common. And so if all of that's true, then you get a little bit simpler equation. This is just comparing that this is a good way to solve it. Even simpler is down here. So this one's in a very special case where everything in the grip is the same material. So it's all steel basically, because your washers are going to be steel. And they went in and on the next page, they did some finite element analysis type simulations and developed these charts, and well, actually they can be different materials. Steel, aluminum, copper, gray cast iron, and just a general expression for the shape of these curves. And they've got these A and B terms. And you can put A and B into this simple equation and get your member stiffness this way. So this one only works in certain conditions where all the material is the same. I'll have to check more closely. It says, what does it say? The entire joint must be made up of the same material. So to me, that also means that the washers, if they're used, are the same material, but you're not going to have cast iron washers pretty much anymore. Copper washers are kind of, sometimes you might have this scenario because there is the risk when you have dissimilar metals, so steel on aluminum, there is a galvanic corrosion possibility when you have two different metals touching one another. So it isn't that crazy that you would have all the same metal touching each other in a bolted joint like this. Lost our page. Oh, there was a picture of a sleeve that I was talking about earlier. I just saw it, like here. So here in this one, when you're doing the bolt or member stiffness, you can't use the Frustum approximation because the Frustum would go, they go outside of the area of the material. So that's what I meant with the sleeve. We are really short on time, so I think I'm going to have to do the calculations for the actual member stiffness in a separate little video like I did with the other thing. That's kind of nice anyway. It kind of keeps it all separate from just the discussion of things. So I'll do that and post that later, hopefully later today, and get this MathCAD sorted out on why it's not giving me the stiffness in the units that I want. So I'll do that, and I'll analyze this one at first because it's one of the more straightforward ones. But then it probably would be good to look at one like this where you have to deal with a different little piece, because this is steel. This is, I don't know what material they have on the top there. Maybe that is steel also. I'd have to read. Different materials. The mirror line of the Frustum is not at the interface between the two different clamp materials, so you've got this little thin layer. So this is more involved, and maybe I'll just work through one like this also, because it would be useful to see how all the different dimensions work out in one like this. I don't have a physical model of one of those like I do for this one though. All right, I will see you actually on Monday. We're going to take all of this knowledge that we've got with bolt and member and joint stiffness. We still have to talk about combining the member stiffness and joint stiffness here. You can tell what we're going to do. We have bolt stiffness, member stiffness. They're in parallel, so we're just going to combine them in parallel as if they were springs in parallel, which is simple to do. All right, on Monday, we're going to use all that and actually do some stress analysis on the clamped members. And then we'll move into fatigue settings. So static first and then fatigue on those clamp joints, bolt threaded fasteners. All right, I will see you on Monday.